Welcome to Math with Professor V. In this video, we're breaking down one of the most confusing parts of Calculus 2, how to decide which series test to use. So I'll start with a quick summary sheet that lists the most common convergence tests and when each applies. And by the way, if you'd like to follow along, I've uploaded these templates to my Patreon so you can download and work through the examples with me. And then we'll jump into examples using the test for divergence, limit comparison, ratio, alternating series, integral test, so you can see exactly how to apply this strategy in different situations. So let's get started. So probably the first kind of series that you went over was geometric series. And remember, if the absolute value of r is less than 1, then the series converges. Diverges otherwise. And you can actually find the sum of a geometric series. This is super rare. And the formula for the sum is it's equal to A. A is the first term of the series, whatever it may be, over 1 minus r. Another kind of series that we learned about was telescoping. This I would only use in the scenario where you're asked to find the sum. So geometric and telescoping are two very unique kinds of scenarios because when they converge, you can actually find the sum. Don't revert to telescoping unless you're asked to find the sum, okay? Otherwise, it's not like a good method to determine if a series converges or diverges. Okay, probably the next test that you learned was the integral test. Remember, in order to apply the integral test, you have to check 3 conditions. Your function needs to be continuous, positive, and decreasing. And then we know based on the result from evaluating the improper integral, our infinite series does whatever the improper integral does. They either both converge or both diverge. Honestly, I don't use this test unless I have to. It's just kind of a lot of work. Integrating isn't always fun, so it's not my default. I don't grab this one unless I'm stuck. Other tests are the comparison test. Direct comparison, limit comparison. Limit comparison is probably going to be your go-to in most scenarios. I use it anytime our series that we're given resembles a p-series with extra stuff. You'll see what I'm talking about. I'll do an example. Or if it kind of looks like a geometric series with extra stuff again, but p-series with extra comes up more. And remember, you can only use limit comparison, direct comparison when the terms are positive. You take the limit as n goes to infinity of the ratio of the terms of your series with the terms of some other series. And as long as that limit is finite and not 0, then both series behave the same. That's a phrase that I use all the time when I'm teaching. So basically, if you compare your series to a convergent series, yours converges. If you compare yours to a divergent series and you get a finite non-zero limit, yours diverges also. So they're just twinsies, all right? Alternating series test, only use it when you have an alternating series. You should see like -1 to the n or -1 to the n plus 1, n minus 1. It doesn't matter. This makes it alternating. And then times some bn. You got to make sure bn's decreasing and the limit goes to 0. If it passes, then by AST, the series converges. Okay, ratio test. Use it anytime you see a factorial. And then other scenarios as well, but if you see a factorial, run to the ratio test. There's no other test you even need to think of. You take the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n, and that gives you L. If L is less than 1, your series converges. It actually converges absolutely. If L is greater than 1, your series diverges. If L is 1, you get no info. When this happens, it's a U problem, meaning you should pick a different test. Okay. Root test is super similar. I don't use it as often as ratio test. So you take the limit, n goes to infinity, nth root of the absolute value of an equals L, same results. And lastly, but actually you should think of it firstly, is the test for divergence. So if the limit of your terms is not 0, then you know the series diverges. Boom. Usually the terms do go to 0, so this gives us no info, but always think about it. This was just really fast and furious. So if you need a more in-depth video lecture or lesson on any of these tests that I've run through, they're all linked in the description, and I have a whole playlist on sequences and series, so that should be your best friend. I also have like a 6-hour video solving 100 questions on sequences and series. You should be able to find almost everything you need on there. Okay, here we go. Determine whether the series converges or diverges. So go through the little checklist from the beginning. This to me is screaming limit comparison. And you might say, Professor V, how do you know that? Well, this looks like a p-series with extra stuff, right? It looks like a p-series with extra stuff. So I'm thinking limit comparison test. What should I compare it to? How do you pick? That can be difficult. Well, all you need to remember is look at who's running the show. Who is the highest degree term in the numerator and who's the highest degree term in the denominator? I have an n squared up top and an n to the fourth in the bottom. You can include the two, you cannot include the two. It doesn't matter. Isn't that cool? So who's running the show upstairs? N squared. What about downstairs? N to the fourth. That simplifies to 1 over n squared. Okay, most likely I'm going to use that for Bn. That's Bn. Now you have to tell the people how you know what the sum of Bn does. And don't forget, you need to write the sum, n equals 1 to infinity of Bn, which is 1 over n squared. Well, what is this? This is a p-series. P is equal to 2, which is greater than 1, so it converges. So now let's go ahead, apply limit comparison test, and just a quick, peek. All my terms are positive, so we're allowed to proceed. So we're going to look at the limit. N goes to infinity, n squared plus n plus 3 over 2n to the fourth minus 9n plus 7 over Bn, which is 1 over n squared. Okay. So when I divide by 1 over n squared, I'm going to end up multiplying by n squared over 1. So this n squared actually comes through and gets multiplied through the entire numerator. So now I have the limit, n goes to infinity. It'll be n to the fourth plus n cubed plus 3n squared over 2n to the fourth minus 9n plus 7. Perfect. So at this step, just check with your instructor. I require my students to show all the steps to arrive at the limit. So if n goes to infinity, numerator and denominator are both going to infinity. What we're going to do is divide by the highest power of n from the bottom, which is n to the fourth in this case. You can't do L'Hopital's rule because the terms of a series are not differentiable. So you don't even think about it. But in certain circumstances, if you're forced to do L'Hopital's rule because there's no other way to find the limit, you do a little aside moment and define a function of x. I've shown plenty of examples where that comes out because it is sometimes necessary, but avoid it when possible. Good? Okay. So if I distribute 1 over n to the fourth, this is going to be 1 plus 1 over n plus 3 over n squared, and then down here we'll have 2 minus 9 over n cubed plus 7 over n to the fourth. So in the numerator, these two terms will go to 0. I'm just left with a 1. And then in the denominator, these two terms also go to 0. I'm just left with a 2. So my limit is 1/2. Okay, great. What do I care about this limit? I just care that it's finite and not 0. And then that tells me that my series, which was the sum, n equals 1 to infinity, n squared plus n plus 3 over 2n to the fourth minus 9n plus 7 behaves the same as the series that I compared it to. What did I compare it to? A convergent p-series. So then I just say also converges by the limit comparison test. I let my students abbreviate. Why not? Okay, make sure you don't forget to justify why you know 1 over n squared, the sum of 1 over n squared converges. Don't forget to write this out. If you just write Bn is 1 over n squared, you haven't addressed what the sum does. This is just a sequence without the sigma. Okay, let's look at another example. You guys tell me, what test should I use? As soon as I see this -1 to the n, I just think, oh my goodness, it's probably time for the alternating series test, AST. All right, so Bn is everything without that alternating part. So B sub n is natural log 6n plus 3 over 6n plus 2. Okay, and I have to check two things. First, I have to check, is Bn decreasing? There's a few ways to do this. So one thing you could do is use the definition and compare Bn plus 1 and Bn. this ends up not being very clear. Bn plus 1 would be ln 6 times n plus 1 plus 3 over 6 times n plus 1 plus 2. And if I compare it with the original, it's not obvious that one's larger, one's smaller. So what to do when you're in kind of a sticky situation, we're going to take a derivative. And you might say, but Professor V, you just said no derivatives for the terms of a series. I know. So what we're going to do is we're going to say, let's let f of x equal ln 6x plus 3 over 6x plus 2, all right? Good. So we're going to take the derivative. If I want to show that the terms are decreasing, this function should have a negative derivative. Before I take the derivative, though, I see an ln. We must use our log properties, expand this sucker. That way, we'll have an easier time taking the derivative, yes? Yes. Okay, so f prime of x, derivative of ln 6x plus 3 would be 1 over 6x plus 3. And then I have to multiply by the derivative of what's inside, which is 6, minus this is 6 over 6x plus 2. And from here, I can tell it's negative. If you want to keep going, that's fine, but you can tell if this denominator is larger than this one and they have the same numerator, this must be smaller. Smaller minus something bigger is negative. But if that didn't pop out at you, what you would do is get a common denominator. Okay, it's fine. You can keep going. No one will be mad at you. And then we have here 36x plus 12 minus 36x minus 18. Don't multiply out the denominator. Don't do it. Okay, and then here we go. 36x cancels. And then I've got negative 6 over 6x plus 2 times 6x plus 3. Now, remember, we're only plugging in values of x that mirror the values that n can take on, which is from 1 to infinity. So I know these terms here in the denominator are not going to be negative. This is actually positive, and I have a negative numerator. So a negative divided by a positive, that's negative. Okay, so since f prime is negative, that means f is decreasing, which means b sub n is decreasing. Woohoo! Hopefully the next condition's easier to check. What's the next condition? I need to check what's the limit as n approaches infinity of b sub n. So what's the limit? N approaches infinity, ln 6n plus 3 over 6n plus 2. Since n is approaching infinity and it's taking on values from 1 to infinity, natural log is continuous on that interval. We can pass the limit through. So we have ln of the limit as n goes to infinity, 6n plus 3 over 6n plus 2. And then from here, go ahead, divide everybody again by n to the first, divide by n. And then we have now natural log of the limit as n approaches infinity. This is 6 plus 3 over n over 6 plus 2 over n. Both 3 over n and 2 over n go to 0. So 6 over 6 is just 1, and ln of 1 is 0. Boom. So both conditions of AST were satisfied, so then I can say with confidence the sum n equals 1 to infinity, negative 1 to the n, ln 6n plus 3 over 6n plus 2 converges by the alternating series test. Okay, perfect. Next one, can you tell what test is appropriate to use? As soon as you see factorials, your brain should go straight for ratio test. Oh yeah, ratio test. Don't even think about anything else. So limit, n goes to infinity. You need absolute value, a sub n plus 1. Be careful. 2 times, put parentheses on that n plus 1 factorial, over 9 to the n plus 1 factorial. And then this all gets divided by a sub n, the original, 2n factorial over 9 to the n factorial. Okay, now nothing's negative, no alternating terms, so I'm just going to switch to parentheses. I don't have to keep absolute value. This is limit, n goes to infinity. This 2 distributes. So now I have 2n plus 2 factorial over 9 to the n plus 1, n plus 1 factorial. And then divided by, which means I'm going to multiply by the reciprocal of the denominator. So we'll have 9 to the n, n factorial, 2n factorial. Okay, now we need to break down the factorials and exponents. That way we can have a little cancel party in a hot second. So if you need a review on factorials, I have a video. I'll link it in the description. This you can break down to 2n plus 2, 2n plus 1, 2n factorial. Stop there because see, it'll cancel right here. Perfect. N plus 1 factorial, that's n plus 1 times n factorial. Stop. Now you can cancel. And then 9 to the n plus 1 is 9 to the n times 9 to the first. So now 9 to the n is gone. So who survived this wild party? 2n plus 2, 2n plus 1, they're still standing. And then I've got a 9 and an n plus 1 in the bottom. That's it. Oh, wow. Limit n goes to infinity. 2n plus 2, 2n plus 1 over 9 times n plus 1. Okay, look, the canceling fun just won't end. Take out a 2 from 2n plus 2, and then I have an n plus 1, which cancels. Oh my goodness, I love it so much. So now this is the limit, n goes to infinity. I have a 2 times 2n plus 1, so that's 4n plus 2 over 9. Well, what happens? That just goes to infinity. Very good, which is greater than 1. So then you're done. You just say, whoop, the sum, n equals 1 to infinity of 2n factorial over 9 to the n times n factorial diverges by the ratio test. Excellent. I love all the canceling and I love factorial, so this is my favorite test. Okay, next we have the sum n equals 1 to infinity 4n plus 5 over the square root of 4n squared plus 5n plus 4. So maybe you look at this one and you start having a mild panic attack. I would say this reminds me a lot of the first one where we did limit comparison. I'm just kind of talking you through where my brain would go if I didn't know exactly how to proceed. So then I would think to myself, well, let me try to determine what to compare it to. So who's running the show in the numerator? What's the highest power of n up top? It's just n to the first. And then in the bottom, be careful, you have square root of n squared, which really is just like n to the first. And then you're like, wait a minute, if I simplify this, I get 1. I don't get a p series. And then my mind immediately goes, I bet you the terms aren't even going to 0 then. Let's try the test for divergence. So the test for divergence, remember, if the terms of the series don't approach 0, then for sure the series diverges. So you just literally come here and you take the limit as n goes to infinity, 4n plus 5 over, square root 4n squared plus 5n plus 4. I'm going to multiply everybody by highest power of n in the denominator, or divide, by highest power of n in the denominator, which is n to the first. So let's see, up top we're going to have limit, n goes to infinity. This will be 4 plus 5 over n. And then be careful, when you bring this 1 over n under the radical, it actually becomes 1 over n squared. So now underneath the square root, we have 4 plus 5 over n plus 4 over n squared. So then now when we take the limit, 5 over n goes to 0. So does 4 over n squared. And I'm left with 4 over square root of 4, and this gives me 2. What do I care about 2? That it's not 0. So then that tells me that the sum, n equals 1 to infinity, 4n plus 5 over square root 4n squared plus 5n plus 4 diverges by the test for divergence. Now you guys remember, this is called the test for what? The test for divergence. So it will only ever tell you that a series diverges. If the limit does come out to be 0, the test is inconclusive. You have no info. Pick a different test. It will never tell you something converges. It can only be used to tell you a series diverges. Okay, very good. Sometimes students forget about that one because it's one of the first ones you learn. And it doesn't apply the majority of the time. So I can see why it's easy to forget about it. Okay, last one. All right, let's think. So it doesn't exactly look like a p-series because of that ln of n. And if you try to do limit comparison, you're going to get inconclusive results. Try it. Try it with harmonic. You're going to get a limit of 0. Try it with 1 over n squared. Again, it will not work. So then you're like, oh, shoot, what to do? Sadly, ratio test won't work. Root test won't work. It's not an alternating series. What are we left with? No, nobody asked you for the sum, so don't start thinking telescoping. That's weird. We're going to do integral test. I know. And then maybe you start looking at it and you go, oh yeah, if that became an f of x, I could integrate it. Shoot. Okay. So what we're going to do is we're going to let f of x be 1 over x ln of x. And I have to check that the 3 conditions of the integral test are satisfied before I can proceed. So first I have to check, is f continuous on, in this case, the interval from 2 to infinity? Because notice that matches the index of summation. Well, what's the domain of f? What's the domain of our function? X has to be positive, and also it can't include 1. Very good, because if x is 1, ln of 1 is 0. So it's going to be the interval from 0 to 1 union 1 to infinity. Well, 2 to infinity is a subset of this domain, so therefore it is going to be continuous. Boom. We have a theorem back in Calc 1 that logarithmic functions, rational functions, compositions of them are continuous on their respective domains. Okay, next I need to check, is f of x positive on 2 to infinity? This one you don't really have to do a whole lot. Just sit there and think about it. If you plug in anything from 2 to infinity, yes, my function will be positive. You just put a check mark. 3, you want to check, is f of x decreasing? So what do? We're going to take f prime of x. Oh, for sure. So remember, this is x ln of x to the negative first. So I'm going to do chain rule. F prime of x is negative x ln of x to the negative second. And then derivative of the inside requires product rule. Yep. So derivative of x is 1. Leave ln of x alone. Plus leave x alone. Derivative of ln of x is 1 over x. So this is going to be negative. I'll have ln of x plus 1 over, why so crooked, x ln of x squared. Notice here, this denominator is positive. Ln of x plus 1 is going to be positive because we're on the interval from 2 to infinity. So you don't have to worry about the entire possible set of values you can plug in for x when you're checking the f prime is decreasing. The f prime is negative. You just want to make sure that the values that match with the index of summation will yield a negative derivative. So yeah, like this is positive on 2 to infinity. This is always positive. I have a positive divided by a positive, and then this minus sign outside. So for sure, this derivative is negative. So all of this was to say, hooray, it's okay to use the integral test. Yep. So then now we're going to look at the integral from 2 to infinity, because that matches the index of summation, of 1 over x ln of x dx. So rewrite it immediately as the limit as t approaches infinity, integral 2 to t 1 over x ln of x dx. And then from here, yeah, you can do a u sub or do it in your head, that's fine. So we're going to let u be ln of x, and then du would be 1 over x dx. And you also need to change your limits of integration. So u of 2 would be ln of 2, and u of t is ln of t. Don't forget to do that. So we have limit t goes to infinity, integral from ln of 2 to ln of t. This is u, and then 1 over x dx, 1 over x dx is my du. So we have 1 over u du. Perfect. Now we have limit t goes to infinity, ln, absolute value of u, evaluated from ln of 2 to ln of t. And then this is going to be the limit t approaches infinity, ln of the absolute value of ln of t minus ln of the absolute value of ln of 2. It's positive already, don't worry. Good, good. And then as t approaches infinity, ln of t is approaching infinity. So this whole first term is approaching infinity. This is just some number. I don't care what it is. Infinity minus some number, this limit's going to still approach infinity, which means the integral diverges. This limit would need to be some constant for the integral to converge. So if the integral diverges, then that means the infinite series, n equals 2 to infinity, 1 over n ln of n diverges also, let's tell the people why, by the integral test. Okay. And that's the overall strategy for choosing the right convergence test. So look for the patterns that I mentioned on the first page. And if this video helped, please give it a thumbs up and subscribe. That way you can keep up with more of my uploads and check out the other content that I have on sequences and series. Now, this is brief. If you needed more examples, I have so many videos for you. So like I said, there's the sequences and series playlist, Calculus 2 video lectures, and so much more. Thanks so much for watching, you guys. I'll be back sooner than later. Bye.